Right now, as you are listening to this, your phone or, your computer, it is quietly screaming into the void.
Oh, absolutely screaming.
Right. It is firing off millions of these invisible high-speed negotiations just to keep you connected to this audio. And if even one of those microscopic negotiations fails, or like if a neighboring device talks over yours for a fraction of a millisecond.
Everything crashes. The
Yeah.
whole connection just drops.
Exactly. And we take it completely for granted. I mean, you tap a Wi-Fi network, you plug in a cable, and you just expect the internet to be there.
Yeah, it's the ultimate illusion of simplicity, really. We expect to open a browser and instantly stream a movie in 4K, completely oblivious to the absolute chaos happening down at the hardware level.
Total chaos.
Right. And to make that seamless experience possible, there is...
And that is exactly what we are unpacking today. Our mission in this deep dive is to decode the architecture of local networking. We're specifically pulling from a CCNA Module 6 presentation today.
Which is fantastic source material for this.
Yeah, it really breaks it down. We are going to look at the exact moment right before your data hits the physical copper wires or the fiber optic glass or the radio waves. We are diving into OSI Layer 2, the data link layer.
Yeah, the data link layer, this is where the digital actually meets the physical.
Yeah.
You can think of layer 2 as, well, like the invisible traffic cops, and also the heavy-duty packaging plants living right inside your computer's network interface card.
The NIC.
Exactly, the NIC.
I love that visualization, honestly, because the core definition we are working from today frames Layer 2 as a bridge. It is strictly responsible for NIC-to-NIC communication, right? It takes the pristine abstract data from your software and readies it for the very messy, unpredictable physical network.
Totally. And to pull off that translation between software and hardware, Layer 2 is tasked with 4 massive responsibilities. First, it enables media access.
Which is huge. Right.
Oh, it's everything. It means your web browser or your email client never has to care whether you are using an old copper Ethernet cable or a high-speed fiber link or just Wi-Fi. Layer 2 handles that physical reality entirely.
So the software gets to stay oblivious. What's the second job?
Second, it encapsulates data. So it takes the Layer 3 IP packets, which is the actual payload you care about, and wraps them up into secure Layer 2 frames.
Okay, so it's prepping the package for delivery. What happens after it's all wrapped up?
Well, that leads to the third job, which is exchanging those frames. It actively controls how that package is actually placed onto and received from the literal physical media.
Got it. And the fourth?
The fourth job is error detection. Because, the physical world is noisy. It's full of interference. So Layer 2 checks the data the instant it arrives.
Just to make sure it survived the trip.
Exactly. If a frame gets corrupted by, like, a stray electrical spike, Layer 2 ruthlessly rejects it before it can infect the rest of your system.
So it's essentially shielding the software from the harsh realities of the hardware. But bridging that gap is so complex that the IE 802 engineering standards actually split Layer 2 into 2 completely different sublayers, right? Like it has a split personality.
It does. And it's a brilliant piece of engineering design, honestly. Because think about it, software evolves constantly.
Right. There's always a new update.
Exactly. But hardware takes years to replace. If they were permanently fused together, every time you updated your operating system, you might literally have to go buy a new Wi-Fi card. By splitting Layer 2, they solve that whole problem.
Okay, so we have the upper half, which is the LLC, or Logical Link Control, and then the lower half is the MA, or Media Access Control. If you look at it like a factory shipping department, the division of labor makes perfect sense.
Oh, I love the factory analogy for this.
Yeah, so the LLC is basically the clerk sitting at a desk in the front office. They talk to the software, figure out what kind of package is coming down the line, say an IPv4 or an IPv6 data packet, and they just handle all the logical paperwork.
Exactly. The LLC operates entirely in software. It never actually touches the cables.
But the MAC sublayer, that is the forklift driver down on the loading dock.
Yes. The MAC is implemented directly in your device's hardware.
Right, and the forklift driver doesn't care about what's inside the box or what the software is doing up in the front office. They just physically grab the package, put it on the right kind of pallet, slap a local shipping label on it, and literally drive it onto the delivery truck.
Which is perfect. And that truck could be an Ethernet cable, which uses the IEEE 802.3 standard. Or it could be a Wi-Fi radio wave, which uses the 802.01 standard.
And this is where the plot really thickens, because we have this forklift driver, the MAC hardware, ready to load data onto the roads. But a forklift driver is completely useless if they don't understand the layout of the roads outside the warehouse.
What, they'd just be driving blind?
Exactly. That physical layout fundamentally changes how they operate. Which brings us to the maps themselves, network topologies.
Yes, topologies. This is where it gets really interesting.
It is fascinating because when we talk about the upper layers of the internet, things are governed by software RFCs or request for comments. But down here at layer 2, because we're dealing with literal electricity, light, and radio frequencies, the open standards are entirely defined by heavy-duty engineering organizations.
Like the IE, the ITU, ISO, and ASI.
Exactly.
And they have to be the ones defining this. Because a network card manufactured by a company in Japan has to flawlessly send exact, precise electrical voltage spikes to a router manufactured by a completely different company in the United States.
Right, they have to speak the exact same physical language.
Exactly. If the voltage is off by even a fraction, the data is just destroyed. So these engineering groups map out exactly how networks should be structured.
And when they draw these maps, they make a massive distinction between physical topology and logical topology.
It's the difference between what you can physically touch and how things actually flow logically. The physical topology is the literal, real-world layout.
So if you walk into a server room,
Right, if you walk in, it's the room numbers, the rack positions, the exact ports where those blue Ethernet cables are physically plugged in.
like a literal satellite image of the highways.
Precisely. But the logical topology is how the network thinks it is laid out. It identifies the virtual connections and the IP addressing schemes. It dictates how the frames are actually transferred from node to node, totally regardless of where the cables are physically routed in the ceiling.
Okay, so let's look at the shapes these maps actually take. Network engineers generally divide them into two massive categories. You've got wide area networks, or WANs, and local area networks, or LANs.
Right, WANs and LANs.
So for the WANs, these are the networks crossing whole cities or oceans. There are three main physical shapes. The simplest one is point-to-point. It's just a permanent direct link between site A and site B.
It's basically a straight pipe. Very common, very secure. Then you have the hub and spoke topology. Think of it like a bicycle wheel. You have a central headquarters, the hub, and then all these branch offices connecting to it, like the spokes.
The catch there, though, is that the branches can't actually talk to each other directly, right?
Well, they can't.
So a spoke has to send its data all the way to the central hub just for the hub to turn around and send it right back down another spoke. It seems like a massive bottleneck.
It absolutely can be a bottleneck,
Yeah.
which is exactly why engineers developed the mesh topology.
Yeah.
In a full mesh, every single node connects directly to every other node.
Oh, wow, so it's all interconnected.
Very much so. It offers incredible high availability. If an excavator accidentally cuts a fiber cable on 4th Street, the network doesn't even blink. The traffic just naturally routes down 5th Street instead.
That sounds amazing, but the physical and administrative cost of a mesh has to be astronomical. I mean, if you have 50 buildings, you aren't just trenching one cable to a hub. You are physically trenching cables from every single building to 49 other buildings.
Yeah, exactly. The number of physical ports alone becomes a total nightmare. That's why full mesh is largely reserved for highly critical infrastructure.
Like what? Military stuff.
Yeah, like nuclear command or maybe top-tier financial trading where they can't lose a millisecond. Most standard enterprises just use a partial mesh, where only the most vital hubs have redundant links.
Makes sense. Now, what about the LANs? The local networks inside a single office building or, your house. Because we certainly aren't trenching fiber for those.
No, definitely not. Today, LANs overwhelmingly use a star or an extended star topology. It looks pretty similar to hub and spoke. All the computers in an office plug into a central switch in the IT closet.
Which has to be brilliant for troubleshooting. Like if Bob in accounting runs his chair over his Ethernet cable and breaks it, only Bob loses the internet.
Poor Bob.
Right. But the rest of the star is perfectly fine.
Exactly.
Yeah.
But it wasn't always like that. We used to use a bus topology.
Oh, man. I remember seeing these in computer labs decades ago. Every computer was chained together along one single long piece of coaxial cable.
The infamous bus. It was an absolute nightmare to maintain because it was literally one continuous electrical wire. If anyone unplugged their machine improperly, the entire network went down for everyone.
Wow.
Furthermore, you actually had to install these physical metal terminators at the very ends of the cable.
Right, because if you didn't, the electrical signal would hit the end of the copper wire, physically bounce back, and collide with new data coming down the line. It was just an echo chamber of data destruction.
It really was. And let's not forget the token ring topology, where the wire formed a literal closed circle. Devices had to wait for a digital token to pass by, before they were even allowed to speak.
Okay, actually, that brings up a huge question for me regarding the logical versus physical maps. Let's say I'm in New York and I have a logical point-to-point connection with a server in Los Angeles. Okay. If we look at the physical cables, my data isn't on a straight wire. It is bouncing through dozens of complex intermediary routers all across the country. Can that logical map still really be considered point-to-point?
Yes, absolutely it can. And this is a concept that takes a minute to wrap your head around, honestly.
It's a bit trippy.
It is. But because of serial protocols like PPP, or point-to-point protocol, the two end nodes, your computer in New York and the server in LA, they act as if they are sitting right next to each other on a single wire.
Really? Even with all those routers in between?
Yep. Logically, the frame can only travel between those two nodes. The protocol handles all the messy physical routing underneath, so at layer 2, it operates strictly as a private point-to-point conversation.
Okay, so the logical map lets us ignore the physical mess. That's super helpful. But even if we understand the map, we still have a massive physics problem to deal with.
We do.
If you have 30 computers in an office, all wired into the same local network, the exact same physical road, how do they avoid talking at the exact same time? If two computers send electrical spikes down a shared copper wire simultaneously, those voltages literally mix together and scramble the binary ones and zeros, right?
You've hit on the exact reason Layer 2 requires such aggressive traffic cops. We need access control. And the absolute first rule of access control is establishing the direction of traffic, which we call duplex.
Ah, half duplex versus full duplex.
Exactly.
So half duplex means devices can both transmit and receive, but only one at a time. It's like a walkie-talkie. I push the button, I talk, I say over, and then I let go so I can actually listen.
That's a perfect analogy. And interestingly, while legacy Ethernet hubs use this, so do modern Wi-Fi networks.
Wait, really? Wi-Fi is half duplex?
Yes, your brand new smartphone on a gigabit Wi-Fi network operates in half duplex. Only one device on a specific radio channel can transmit at a given microsecond. If it's talking, it cannot hear.
I have no idea. Whereas modern wired Ethernet switches operate in full duplex.
Which is more like a telephone call, right?
Mm-hmm.
Both people can talk and listen at the exact same time without crossing any wires.
Precisely. And a critical engineering warning here. If you connect two devices, and one is manually set to half duplex while the other is set to full duplex, you create a duplex mismatch.
Sounds bad.
Oh, it is devastating to performance. The full duplex side is just talking constantly, assuming the other side can hear it. But the half duplex side keeps getting interrupted while it's trying to talk, so it registers massive collisions, drops the data, and constantly resets.
Just creating crushing latency.
Crushing.
So assuming we configure our duplex correctly, how do these devices actually share the road on a network?
Well, on a shared multi-access network, engineers design two main ways to handle it. The first is controlled access. This is where each node gets a highly scheduled, guaranteed turn to use the medium.
Oh, this goes back to that legacy token ring network you mentioned earlier. Exactly. It's like being in a meeting with a talking stick. You can only speak if you hold the stick.
Okay, I can see how that works.
It is perfectly deterministic. You will never, ever have a data collision. But it is horribly inefficient.
Because what if you don't have anything to say?
Right. Imagine sitting in that meeting, and a computer has to hold the talking stick for its allotted time, even if it has absolutely nothing to send, while everyone else just sits and waits in silence.
Yeah, that sounds agonizing, so I'm guessing modern networks abandoned that.
They did. They moved to contention-based access, which basically means devices operate in half duplex and just compete for the road.
So if it looks clear, they just floor it.
Basically, yeah.
Yeah.
But naturally, if two devices floor it at the exact same time, they crash. And the engineering standards give us two major ways to handle those crashes. The first is CSMA-CD, which is for wired Ethernet.
Okay, CSMA-ND. Carrier sense multiple access with collision detection. It's a mouthful, for sure, but the mechanism is fascinating.
Break it down for us.
So first is the carrier sense. The computer physically listens to the voltage on the copper wire. If it sounds clear, it transmits its frame. But if another device across the room also listened, thought it was clear, and transmitted at the exact same microsecond, those electrical signals collide in the wire.
Right, and the voltages spike.
Exactly, and both devices instantly detect that abnormal voltage spike. That's the collision detection part. The corrupted data is immediately discarded. But here's the genius part. They don't just immediately try again because they just collide again, right?
Right, it would just be an endless loop of crashing.
So both devices run a math algorithm to generate a completely random wait time, usually just a few milliseconds before they attempt to listen and transmit again. I've always pictured CSMSD like a polite but incredibly awkward dinner party.
Oh, how so?
Well, two people start talking at the exact same moment. They both hear the collision, they both abruptly stop, they wait a totally random second, and then one of them tentatively says, "Oh, sorry, you go ahead."
That is exactly what is happening on the wire, millions of times a second. It's so awkward, but it works. But here is the catch. You can't do that on a wireless network. Wi-Fi uses CSMA, which is collision avoidance.
CA instead of CD, because it's radio waves, right?
Exactly.
If a Wi-Fi router is blasting data out of its antennas, it's screaming. It can't simultaneously listen for a subtle collision from a laptop across the room. It would just deafen itself.
Spot on. So on Wi-Fi, you have to avoid the crash before it ever even happens. When a wireless device wants to transmit, it doesn't just listen and go. It sends out a tiny header frame that announces the exact time duration it needs to channel.
Wow, okay.
Yeah, it basically tells every other phone, thermostat, and TV on that whole network, hey, I need the airwaves for exactly 4 milliseconds.
So if you're listening to this on Wi-Fi right now, your device is essentially standing up at that dinner party, tapping a glass and shouting, "I am going to speak for exactly 2 minutes."
And just ensuring everyone else in the room stays perfectly quiet until it finishes. That's exactly it. And because radio waves are invisible and can be blocked by walls or, microwaves, the sender needs proof.
Right. How does it know anyone actually heard the announcement?
After your device sends its data, the receiving router sends back an acknowledgement, an ACK frame. Basically says, I got it. If your device doesn't get that ACK, it just assumes a collision happened anyway and starts the whole announcement process over.
It is absolutely staggering that this polite dinner party protocol is happening fast enough to let us stream live video.
It really is a marvel.
So we understand the roads, we understand the traffic rules. Let's finally look at the package itself, the data link frame.
Every frame at Layer 2, regardless of whether it's Ethernet or Wi-Fi,
Yeah.
has three fundamental parts. You have a header, the data payload itself, and a trailer.
The trailer is what really caught my eye in the deep dive material because the upper layers of the OSI model, like Layer 3 or Layer 4, they just wrap data in headers. They put an envelope around an envelope.
Right, it's just headers all the way down.
But Layer 2 is the only layer that puts a cap on the end of the data, this trailer.
Well, it has to, because Layer 2 is the absolute last stop before the data is shoved out into the harsh, interference-heavy physical world. It needs structural integrity. Let's look at the actual anatomy.
Sure, walk us through it.
At the very front of the header, you have start and stop flags to tell the receiving NIC exactly where the frame begins.
Yep.
Then you have the addressing fields. You have the type field, which acts like a label, telling the receiver what kind of Layer 3 packet is inside. Like, hey, this is an IPv4 packet.
Okay, so it's labeling the contents.
Right. Then you have control fields for quality of service, then the actual data payload. And finally, you hit that trailer, which contains the FCS, the frame check sequence.
The FCS. This is the ultimate quality control. It's entirely built around a mathematical calculation called a CRC, or cyclic redundancy check, right?
You got it. Before the forklift driver sends the frame out, the network card runs this really complex polynomial equation on all the binary ones and zeros of the frame.
Oh, okay.
It takes the resulting number from that math and literally stamps it into the FCS field in the trailer. Then the frame goes across the wire. When the receiving network card gets it, it runs the exact same math equation on the data it just received.
And if the numbers match, it knows the frame arrived perfectly intact.
Exact.
But if even a single one got flipped to a zero by, I don't know, a burst of static electricity from a vacuum cleaner near the cable,
Then the math won't match.
yeah.
And the receiver doesn't try to fix it. It just drops the frame entirely. It kills it on the spot.
Wow, it's just ruthless.
Very ruthless, but necessary.
Now let's go back to the addressing field in that header for a second, because I really want to challenge this concept. Layer 2 uses physical addresses, which are universally known as MC addresses. And the architecture specifically mandates that the destination MIC address is the very first piece of information in the frame header.
There is a highly mechanical reason for that placement, actually. By putting the destination MASH address at the absolute front, the receiving network interface card can start reading the frame the exact microsecond it hits the wire.
Oh, I see.
Yeah, if it reads that first MA address and realizes, hey, this isn't my MA address, it just stops listening. It ignores the rest of the frame. That saves massive amounts of CPU processing power.
Okay, the placement makes total sense, but I want to push back on the very existence of the MA address.
For
I just don't get it. We already have IP addresses, right? Layer 3. With IPv6, we have enough IP addresses to assign one to every single atom on the surface of the Earth.
We really do. It's an unfathomable number.
Right. So if we already have a unique IP address to identify every single computer, why on earth do we need to invent a second address, the MA address down at Layer 2? Isn't it completely redundant?
This right here is exactly what trips up network engineering students. And honestly, understanding this is one of the biggest aha moments in all of networking.
Okay, lay it on me.
They serve completely different purposes. The IP address is logical, is the final destination on the globe. And your IP address changes.
Wait, it changes?
Yeah. If you close your laptop at home and open it at a coffee shop, your IP address completely changes based on that new network you connected to.
Okay, right. But my MS address.
Your MSC address is physically burned into the silicon of your Wi-Fi card at the factory. It is a physical serial number. It never, ever changes.
Got it.
But here is the critical limitation. A MAFIS address only works on the local network. It physically cannot cross a router.
Okay. So how do they work together to actually get a web page to my screen?
Think of it like the Postal Service. If you write a letter to a friend across the country, the IP address is the final postal address written in ink on the envelope.
Sure.
That address never changes for the entire trip. But the MS address, that is the local, turn-by-turn driving directions given to the mail truck driver for just one specific leg of the journey.
Wait, okay, let me walk through this to make sure I have it. Let's say I'm sending an email from my laptop to a server in Japan. My laptop's software builds the IP packet. The destination is the IP address in Japan. That's the envelope.
Exactly. You've got the envelope. But your laptop's MC layer knows it can't reach Japan directly. It only knows what is on its local Wi-Fi network.
Okay.
So it wraps that IP packet into a layer 2 frame. The destination MC address, the local MC address of your home Wi-Fi router.
Okay, so the frame shoots through the air to my router. What happens to the frame then?
Well, your router receives it. It looks at the MC address and says, yep, that's for me. And then it completely destroys the layer 2 frame.
It destroys it.
Completely. It strips off the header, it strips off the trailer, and just throws them away. Looks at the exposed IP packet inside and says, the final destination is Japan. I need to send this to the ISP's router down the street.
Oh, wow.
So your router builds a brand new layer 2 frame. The new source MC is your router. The new destination MC is the ISP's router.
Wait, really? So the original frame my computer built never actually leaves my house?
Never. It never goes further than your living room.
That is wild. So it gets destroyed at the very first hop, and then at the ISP, that router destroys it again, reads the IP, builds a new frame for the fiber optic line to the next city.
Yes, at every single router hop, from your house to the city hub, across the oceanic cables to the data center in Japan, the router accepts the frame, destroys it, reads an eternal IP address, and then re-encapsulates that data into a brand new data link frame with local MT addresses just to get it to the next building.
That completely changes how you visualize the internet. The IP address is immortal, but the layer 2 frames are essentially like mayflies. They live for one single jump, die, and are reborn.
They really are. And that is exactly why we need Layer 2. It handles all the dirty, messy, specific realities of moving data over a physical medium, so the global internet layers never, ever have to worry about it.
That is just incredible. So to bring this all together for everyone, OSI Layer 2, the data link layer, is the essential, hardworking translator between your software and the physical universe.
The absolute workhorse.
Right. It uses the LLC and MNIC sublayers to map out physical and logical topologies. It polices the traffic using rules like CSMA and CSMA to prevent data from crashing into itself.
With that polite dinner party protocol.
Exactly. And it meticulously packages IP data into frames, using local MA addresses to guide them on a single perilous jump before starting all over again.
It truly is the unsung hero of global communications.
It really is. And I want to leave you, the listener, with a final thought to ponder next time you pick up your phone. Think about the sheer terrifying scale of this mechanism.
It's almost too big to comprehend.
It really is. The next time you casually load a web page or stream a video, realize that you are commanding millions of microscopic invisible frames to be meticulously constructed. Every single one is running complex polynomial math in its trailer to check for physical damage.
Every single one.
And every single one of those millions of frames is being completely destroyed and rebuilt from scratch over and over at every single router hop across the globe. All of this happening in fractions of a millisecond, just so you can watch a video without buffering. It turns the mundane act of getting online into a continuous, mind-boggling mechanical miracle.
A miracle that happens a billion times a second.
Thanks for taking this deep dive with us. We'll catch you on the next one.